Hello, welcome back, everyone. Let's then start today talking about chapter 12, the last chapter of our wonderful book, Digital Image Processing. Thanks for coming. There is one person in the room. Can you hear me fine, Ziwen? How's the sound? Okay, great. Thanks. So we're going to start today with chapter 12 and probably finish that next week again. This is a long chapter, slow to it, and the second half is about machine learning, or more specifically, one particular algorithm of machine learning, which is neural networks. Or I'd say it's a class of algorithms, not only one algorithm, it's a class of algorithms of neural networks that includes what's so-called deep learning that's so famous today. We're gonna dedicate next lecture only for neural networks and deep learning. I have to warn you that neural networks is just one algorithm, one class of algorithms in the subfield of artificial intelligence called machine learning, and that machine learning is just one subfield of artificial intelligence. There are many others. So what you're going to see, not today, because today we're going to talk about the basics of pattern recognition, but next week is only a small portion of artificial intelligence. So if you are interested in this field, I strongly recommend you to go and fetch a book or a good book, or do an online course, or come and talk to me, and maybe we can have the final lecture of this course as a brief introduction to all the fields of artificial intelligence. There might be space for this. Let me know if that interests you on the flow side, on the general discussions. So, okay, again, let me fix my display settings before we go into the proper lecture today. Right, so what's image pattern classification? Basically, what I want to do is, given an image, I want to tell what this image is, or what's inside of this image. There are many ways of doing this. So as I said, what classification deals with using a set of features as basis for assigning class labels to unknown input patterns. This is the general case of pattern matching or pattern classification. There are three categories that we're going to see. Two of those, 1 and 2, we're going to see today. And as I said, the third category we're going to see next week. So the first one is matching unknown patterns against specific prototypes. Basically, what we're going to find unique patterns in an image. And then if I know the pattern, if I know the prototype, and I got the best matching with the image, I can then classify that pattern found in the image according to the prototype. Optimum statistical classifiers. We've started seeing a little bit of statistical classifiers last week, which is PCA. Well, PCA per se is not a classifier because it doesn't classify things into known classes, but PCA is used as one part of this statistical classifiers. It's intrinsically connected with one particular kind of statistical classifiers, which is the Fisher linear discriminant analysis. We're going to see a brief introduction. Actually, a third of the lecture today will be dedicated to the Fisher linear discriminant analysis. And neural networks, which has as ultimate goal, and that's what the deep learning does today, especially in the shape of convolutional neural networks, which is the neural networks learn the features and then classify it. And that's why they are very famous. And we are going to see that they're not magical beings, they're not unicorns in artificial intelligence. So still need quite a lot of human input to neural networks, but they solve quite a lot of problems. Problems that 10 years ago we just dream about solving. Well, 1 and 2 that we're going to see today use the nature of data as is well understood, leading to an effective pairing of features in classifier design. So basically, for the initial classifiers 1 and 2, and let me get a pointer here. So for 1 and 2, you know what the pattern is, and we give the right features for the pattern classifier, right? For 3, then it actually learns the features, right? So pattern class characteristics features are learned by the system. That's what a neural network does. So what are patterns? There are 2 ways of inputting patterns into a pattern classifier, one is that your data can be labeled. It means that we know the class of each pattern, such as a character recognition system. So if I want to develop a system that sees by using a camera a handwritten digit, and I want to classify this digit, of course, the system doesn't know a priori what this digit that it's looking at is, but it's been trained with label data, meaning that it's been assigned, it's been trained with a number of images from various digits, and each one of these images are labeled with a particular class. So a handwritten number 1 is labeled with the class 1. So the system is given a whole bunch of digits 1 labeled 1. And the same thing for 2, the same thing for 3, and so on and so forth. So you train your classifier with label data. And then if you want to recognize something that the classifier hasn't seen before, a digit that the classifier hasn't seen before, an input that the classifier hasn't seen before, then this is called supervised learning. But you can you have as input unlabeled data, meaning that you only know that the data refers to patterns, right? You only know that the data refers to patterns, but you don't know what the pattern is. You don't know the actual classes. So what you want to learn is what are the classes first? What are the classes of patterns? What are the labels of the pattern? The labels are not known. And basically, these kind of algorithms work by seeking clusters in the data set, with the aim at using the cluster centers as pattern classes. You can we discussed something related to that last week. So imagine that you have like a feature space. Remember that we discussed about feature spaces last week? So let's see, we have a bunch of figures. That's a little star, a little circle, and a square. So you show the system a number of, you don't know the labels. So you don't know that this is a star. You don't know that this is a circle. You don't know that this is a square. You just give them pictures. But you know that the I star has a particular set of features that are different from a circle, that are different from a square. So meaning if you get a number of features, it could be on n-dimensional space. It doesn't need to be on 3-dimensional space. You can have n features, and you get a bunch of figures of hand-drawn stars. They are going to fall on one particular portion of this space. Or, for instance, a circle would fall on another portion of this space. A bunch of images of feet of circles. And for instance, squares could be in another portion of this space. So what your image classifier, or what your classification system is going to do, first, these data points are not labeled. So first, it's going to find the cluster centers. These kind of algorithms are called clustering algorithms. So they're going to find cluster centers. And this will be then your classes. So the first thing that your algorithms are going to do, they're going to find these classes. And once they find these classes, they know how to classify, right? So if the system is given this star, certainly this star will fall somewhere around this space. And just by minimum distance, you get the distance from this cluster center to this point, and to this cluster center to that point, and to this cluster center to that point, and get the minimum. And you're going to see, oh, my star is just horrible, but it's certainly going to be closer to a star than to a circle, right? So the minimum distance will be to a star, and I would be able to classify it into class C1. Is that clear, right? So that's unsupervised learning. So basically, you know that your data refers to patterns, but you don't know the class of each pattern. The class of each pattern is unknown. So basically, what the systems do is to see clusters in a data set with the aim at using the cluster centers of pattern classes. Okie dokie. And okay, so these are in general, general terms, what a pattern classification is. What are the general methods for pattern classification is? But what I want to talk with you seriously now, and that is the most important bit of this lecture. If you want to take one bit of this 2-hour lecture, that's the stuff that I'm going to talk now to you, which is how you train and evaluate a classifier. I've seen loads and loads and loads of mistakes done in this sense, and the mistakes are really horrible. So you basically think by people publishing crap, total rubbish papers, people at the industry doing a total mess with the results because they don't know these concepts. So please pay attention to this. So basically what you do, once you get a data set, and it could be a data set of, labeled data or unlabeled data. The first thing you have to do, you have to decide to divide it. So your data set should be divided into training set, validation set, and test set. Don't forget about it. Your training set should be totally distinct from your validation set. They should be totally distinct from your test set. So there are many strategies for doing this, for dividing the training set, the total data set that you have into training set, validation set, and test set. The usual thing to do is you get 50% of your data set is going to be used for training your model. So it's going to be used for training your model. Then 25% will be used for validating your model. And the remainder 25% of your set is used for testing your model. Right. So what does it mean? So basically, what the pattern classifier is doing, it's learning these models, right? It's learning. So you're going to use this training set, large portion of the data set that you have, to create a model. So the goal of this part of this training set is to adjust the parameters in order to assign the right class to the appropriate example data item. So basically, what it's doing here, I have to draw that picture again because this is important. So if you have, let's see, you have unlabeled data, you have unsupervised training data, you have an unsupervised learning. and you are learning these clusters, right? And you use what? These dot points that I'm using here, these are training data. With this training data, then I find the parameters of my clusters. So I find the cluster center and some sort of as a Gaussian. I'm adjusting a Gaussian to this data. All right? So once this is done, you forget about your training data. You don't use your training data for validation or test. So what are you going to do for validation test set? You are going to get a distinct 25% of your example of your data set that hasn't been used on training. And I repeat, none of these points in the validation set can be used in training. So it's a totally distinct data set. So that you're going to try it out. So the system hasn't seen these examples, right? The examples in the validation set. So you're going to get, remember, I star failed here, and then you check whether your system classified this star correctly. What if your model doesn't classify points in the validation set correctly? You change your model. You change your model parameters. So you use the validation set to get a better model. This is important. You use the validation set on trained model to enhance your model, to change the model. So you're going to train again and do the whole thing, training set, validation set again, until you get a very good model. And now, the next step is you're going to test your model. Again, this test set, the data in this test set is totally independent from the validation set and from the training set. So this is like you are testing the test set, you are testing your system in the wilderness. You are sending your system to the wilderness, and you're seeing, well, then you want to check the behavior of the classifier with unseen data, right? So basically, this is going to tell you, the test set's going to tell you how your model is going to behave on the real world. So you don't use your test set for changing your training model. That will be cheating, right? So you're going to, and then what you're going to publish is the results that you get from the test set. What you're going to publish, or what you're going to use as the characteristics of your model, are the results that you get with your test set, right? So never forget that if you have a classification problem, you should divide your data set into 3 distinct sets. One for training your model, one for validating your model, which you are going to use the results to get your model better, and one for testing your model, right? So I've seen mistakes done in this way by people that have not respected this separation, right? So what if your training validation results are good, acceptable, but then your test results are not? This occurs more often than not. This is what we call, it's an overfit. We say that the training was overfit. Basically, this indicates usually that you're using the wrong architecture for the problem that you have at hand, or that you have a small data set, or that you have a very noisy or biased data set, and something is wrong. So if this happens, so your training and validation results are good, but your test results are not, there's something wrong with some things that you've done, either with the architecture or with a small data set or with a noisy data set. All right. So I can't say more that this is the most important part of the whole course. I wouldn't say only the whole lecture, the whole course. Not only because it's applied to machine learning, but to vision, computer vision, and image understanding and image processing, but also to any machine learning project, any classification problem that you have at hand. So take it home and never forget that. So another thing that you should that's also important for you to take home, as important as this separation between training set, validation set, and test set, is the classification metrics. These are very important, and you wouldn't believe how many people don't know about it. Don't know. It's unbelievable. I went to Germany, to one of the best universities in Germany. It's Bremen University. I gave a short course there, and people that didn't have a clue about these classification metrics. In that particular clique of people that I collaborated with. So some of the key methods for classification metrics. Accuracy. Pretty sure most of you have heard accuracy or have heard or used the term accuracy before, right? But there are other methods as well which are complementary to accuracy, which is recall, precision, and the F1 score. So we're going to assume a model, a binary model of evaluation here. Either your answer is correct, so where classification gave you the correct answer, or it's incorrect answer. But any concept that I'm going to be dealing with in this lecture could be applied to any sort of model evaluation. That you could have many classes, but let's just assume that we have binary classification. So the classifier said yes or no. It's a yes/no question, right? So yeah, the yes question, the yes answer that the classifier gave could be either correct or incorrect. Okay, so after training the model, then respecting all of this stuff that I talked before. So after training the model, we want to evaluate it. So let's assume that we have non-labels, that we have a supervised learning here. So we input a validation example, such as the image of a dog. I have a classifier that classifies cats and dogs. I get the output of the model classification. Basically, the answer, is it a dog or a cat? Let's assume we want to classify dog. We want to find all the dogs in the data set. So the output of the model, if I have two classes, I only have 2 to the power of 2 classes, possibilities, right? Where either the input is dog, is a dog image, and the output is the class dog. This is called true positive. The input could be an image of a cat, but your classifier made a mistake and said this is not a cat, this is a dog. So the output, this is a false positive. Why? Because if I want to classify dog, and the output is a positive class, right? It's the dog class that I'm looking for. But the output is false because the input was a cat. So this is a false positive, right? I can have the other way around. So the input is a dog, but the output is a cat. So the system sent a negative answer. So this is not a dog, but that's a false negative answer. So this is a false negative. And the input could be a cat, and the output a cat. So this is a true negative, meaning this is not a dog. The input is not a dog, and in your classifier said it's not a dog. So this is a true. It is a true negative, right? So you have to repeat it to all the validation data and then later to the test data. And you're going to count the total number of true positives, true negatives, false positives, and false negatives. It is with these parameters that we're going to calculate a number of metrics. Okay, so accuracy is one of them. Accuracy is the simplest, the one that people use at length, and especially students, and one that's wrong in most of the situations. And we're going to see why it's wrong in most of the situations. Not all, of course. I'm not saying that accuracy is wrong, but I'm saying that you should learn how to use accuracy. And because there are other metrics that are better to evaluate a classifier. So accuracy is basically the number of correct predictions divided by the total number of predictions. So number of correct predictions is a there is a mistake here. Let me solve it now. The number of correct predictions is not what I've written. It's not the number of true positives. It's the number of true positives plus true negatives, because true negatives is also a correct prediction, right? So because this, in our example, this predicted that the dogs are dogs. The images of dogs were classified as dogs. And this predicted that image of cats were classified as cats, as not dogs. Divided by all of the predictions. All of the predictions were divided by the sum of true positives, true negatives, false positives, and false negatives. Right? So whenever I do that, I have to fix the display settings. Just a second, people. Okay, so this is useful. Accuracy is useful if the target classes are well balanced. So for instance, if I have the exact same number of cats and dogs images of positive and negative examples, or of any sort of classes, if I have n classes, I should have a well-balanced data set. It's not useful if the data set is unbalanced. So if I have 99% images of dogs and 1% of cats, because then a very simple model, such as a model that only says everything is a dog, has 99% of accuracy. But it's a really, really bad model. So accuracy doesn't see it. Accuracy assumes that your model is well balanced. So in more general ways, for more general problems, the metrics that we're going to use are precision recall. Precision recall. So what is recall? Recall measures the extent of which the model finds all the relevant information. So basically, the number of true positives divided by the number of true positives plus the number of true negatives. So if I want to classify only dogs, as it was my goal, I want to see how many times it classified the class that I'm interested in, right? And precision measures the extent of which the model finds only the relevant information. It's basically the number of true positives divided by the number of true positives plus the number of false positives. Right? So, while one is the number of what is the percentage of relevant information that my model found given the true answers. This is the proportion of model given the true answers. This one is the proportion of true answers given the true answers and the points where the model replied wrong to true positives, right? So you see that there is a trade-off here. Again, while precision measures the proportion of actual relevant data points your model says is relevant, recall measures the ability to find all relevant instances. So we're going to see in papers that curves of telling precision recall, putting in a graph the rate of precision recalls are very useful analysis tools in image classifications. And then another metric is the F1 score. F1 score basically measures this trade-off between precision and recall. And it measures that by just getting the harmonic mean between the precision and recall. It's just by applying this harmonic mean formula. So why not we take the average between precision and recall? Because basically the average does not punish extreme values. So imagine that I have a precision 1. Basically, it's 100% precision, but a recall of 0. The average then would be 0.5, whereas the F1 score is more truthful to the nature of my classifier, right? The F1 score will say that my classifier has 0, Okay. So, and we can use this idea of confusion matrix to put everything in one place and to extract other metrics for our classification. So basically, what we have is that on one side of this matrix, there is the true condition. So these are the label data. These are what we call the gold standard. So I know the cases, I know the right label for my example, the right positive labels and also the right negative labels. And now this side here is the rate printed of positive cases and of negative cases. So this one, I know all the labels. If taking our examples of cats and dogs, for condition positive, I know all the images that have dogs that are dogs. And I know all the images with cats that are cats, and they are labeled as cats. And this is the output. This is the predicted condition. This is the output of my system. So if my system says to given an image, if the system says this image is a dog and it's a correct condition, it's a correct label, it's called a true positive, right? If the condition is a dog, a positive condition, but it says that it's instead a cat, this is what I call a false positive, or also known as type 1 error. If you're going to go work on medical data, they talk all the time about type 1 error rather than false positive, right? So, and the same thing for the predicted condition. So this, your system, your classifier predicted an image as a cat, and it's in fact a cat, then it's a true negative. If your system predicted the image of a cat with the label dog, that's a false negative or type 2 error. And well, I do recommend you all to read the Wikipedia entry on precision recall. It's really well written. It's really well written. Not everything on Wikipedia is very good, but this one I recommend. Right? And these graphs, these tables I took from there. So you're going to see there's enough of metrics that we can extract just from this very simple confusion matrix that just counts the number of true positives, false positives, true negatives, and false negatives. So you see that recall is here, is the sum of true positives divided by all the conditions that said positives. Whereas you have false negative rates, you have false positive rates. Specificity is another metric that has is the complement of specificity is the complement of recall, or also known as sensitivity, with the rate of true negatives divided by the sum of all conditions negative, all the answers that are negative. Accuracy is here, as we've seen. So accuracy is here, and the precision is here, right? And there's other metrics as well: false omission, positive likelihood ratio. So these are all rates that you take out of this very simple confusion matrix. And there is a number of metrics. So an F1 score is here, right? A diagnostic odds ratio. So then you may ask me, when would I apply one and when would I apply another? That basically depends on the kind of problem that you have. And that I've done it many times with various graduate students. Have various papers that use these metrics, and every time that we get data, that we get a confusion matrix, we have to sit down and analyze the problem. So that's where the science kicks in, right? So you have to understand the problem, and to see, well, understand the problem and understand your confusion matrix, and then see which one of these metrics is actually more suitable to make your results visible, right? So actually analyze your results. Unfortunately, we don't have time to do that in this topic. It would be good to have a data set or various data sets from distinct applications, run them over a classifier, and then discuss when do I measure precision recall, when accuracy is the right metrics to use, when we use F1 score, and there are other metrics as well as ROC curves, ROC curves, and so on. Right, a simple example that's used everywhere. We found it on this link, but I've seen this example in various books, so it's a very common example. So imagine then that you have a case of a classifier system that classifies molds or images of molds into potential cancers, potential cancer, cases of cancer, and not cancer. So you see, this is the other way around. Predicted or model is on the column, but the actual label is on the line, right? So you see that your system said, in this case here, the system says that the image of mold was a no case of cancer 50 times, given a data set of 165 data points, and it got predicted correctly. Sorry, it got predicted correctly as no case of cancer 50 times, and it got right. So said this mold is it predicted as a real case of cancer, and it was actually a real case of cancer 100 times. But it made a mistake of saying that a mold that was actually a case of cancer, it said no. So this is a quite dangerous point here, and that's why in medicine they call it type 2 error. Type 2 error, you want to get them the smallest as possible. You want to get this as minimal as possible as type 2 error. Why is that? Because you don't want to send a person home that has an actual case of cancer, but then just because your system predicted no, and you're not going to look at it anymore. So you prefer to err on the case of your system predicting more cases, so making more type 1, meaning that the mold was a no case of cancer, but the system predicted that it was a case of cancer, because in these cases you're going to do more analysis, right? You're going to get a biopsy or other sorts of analysis to make sure that that case was an exact case of cancer. So in medicine you prefer to err on type 1 errors than on type 2 errors. Okay, and based on this classifier, you can get the accuracy. Just a numerical example. It's basically a division, right? You get the rate of true, the number of true positives plus negatives divided by the total number of cases. Precision is the true positives divided by the true positives plus the false positives. Recall is the true positives divided by true positives plus false negatives. Right? Yes. So again, I know if that's the first time that you've seen this, this may be a little bit confusing. And I do recommend you to read the Wikipedia entry on that. So today I've just donated $2 to Wikipedia, and I always donate $2 to this page to Wikipedia just for maintaining this page. It's really good. And well, of course there are There are other literature about it, and it gets really complex, especially when you're dealing with medical data. It gets really complex. But for now, and for the purpose of this topic, just get used to this confusion matrix and there's three metrics, four metrics here, which is accuracy, recall, precision, and F1 is score. And again, if you need to take one thing home from this lecture today, it's this, right? So it's this stuff. Exactly two things, right? That you should divide your training set into your data set into training set, validation set, test set, and these are classification metrics, which are the most basic classification metrics, and the confusion matrix. Please don't forget the confusion matrix. Get confused with confusion matrix. Okay, so let's see a number of simple algorithms and leave neural networks with slightly more complex for next week. Let's understand what are patterns and pattern classes. Most traditional pattern arrangement that we see all around that's used for in the statistical classifiers are the pattern vectors. So basically, a pattern vector then can be seen as a point in n-dimensional Euclidean space. Then a pattern class can be understood as a hypercloud of points in this pattern space. A pattern can be formed directly from an image by vectorizing using linear indexing. So basically, if I have an image like that with these intensity levels, so I can transform it in an image into a pattern vector by just following this linearization. So this pixel then becomes the first element of this vector. This becomes the second, and this is the third. This is the fourth, and then when I come back to here, when I come here, I go to the top, and that will be 175 here, and so on until the end of the image. Examples of pattern recognition and feature vectors. One of the most classic examples that was used by Fisher, the same one that created the linear discriminant analysis. Actually, Fisher created the linear discriminant analysis very early on the 20th century, around the 30s. So the problem is the recognition that Fisher used and these data sets used until today as examples of image classification problems is the problem is the recognition of three types of flowers. It's iris flowers. There are three types. It's iris setosa, iris virginica, and iris versicolor. And basically what Fisher did, he used four features: petal length and width. Basically, these flowers, they have a sepal and the petal. Don't ask me what's the difference between a sepal and a petal. I'll ask a biology person. If you understand, please send me what's the difference between a sepal. But you know that the sepal is that exterior. I would say petal, but it's not a petal in the flower. And the sepal, it is an interior petal in the flower, right? So he used the petal length and width, and also the sepal length and width, and placed that into a feature vector. And then I use that as features to allow the classification of what? Of either this image. Here we're talking about image. Fisher was in 1936. He was talking about actual numbers, right? Not that an image is not a number, but measurements. So he was doing measurements on these petals and sepals and having data sets and doing all the classification by hand. This is called the Fisher iris pattern classes. You can we're gonna see an example of a pattern classifier running on this recognition problem. But first, let's just have a look at all the features that you can use. So you can use all the pattern descriptors that we've seen last week or in the last 2 weeks, right? Everything that we've seen on chapter 11. So your pattern vectors could be formed from this description of boundary shapes, right? And remember that we've seen this is a signature of a boundary shape. So basically, this could be your pattern vector. So basically, by expressing the signature as a vector, sampling its amplitude at increments of angular increments, then forming a vector by letting every value, every item of every element of this vector by being exactly this the output of this function, right? The radius with respect to theta. So we transform this signature that we've seen as a feature last week into what? Into a description of this figure that then becomes a pattern vector. Vectors can also be formed by boundary and region features. Remember that? This stuff that we've seen last week or the week before, the stuff on chapter 11. So we could use the pattern vectors as compactness, circularity, and eccentricity of these figures, as I've done in the first example that I gave today. Vectors can also be formed by features from properties of image regions. So remember that from what we discussed, that we can get an image region here, and then this will be, I could run a number of texture metrics. So this could be each one of those texture metrics that we've seen last week could be one element of the feature vector of your or other pattern descriptors. These invariants to rotation and scaling that we've seen last week. When working with the sequences of registered images, we can use the corresponding pixels as patterns. Remember that what we've talked about with respect to the PCA last week. So that with PCA we created these vectors. I didn't call it pattern vectors because at that time we were interested in using PCA as a feature descriptor. In this case, now the same thing that we did before last week with the principal component analysis, we can use the same input as pattern vectors. And finally, entire images could be used as input to the pattern recognition system. That's basically the task. That's basically the gain that deep convolutional neural networks gave to the science, brought to this field. And we shall see it very, very soon, probably next week. Okay, so we're going to see a few examples of algorithms. There is one class of algorithms is this called prototype matching. It's basically defined on comparing an unknown pattern against a set of prototypes figures and assign to the unknown pattern the most similar class of prototype. It's a very, very simple idea, right? And quite a few methods. They are basically mostly applied in industrial situations. No one in this industry that I know of use these very advanced methods as deep convolutional neural networks. It's like killing a fly with a cannonball, right? We use simple methods such as another widely used method is minimum distance classifier. I've seen it used in various applications. And matching shift features you may have imagined, right? So in our discussion about the shift method, we did some matching, right? So basically that's shift, and the matching shift features is understood as a kind of prototype matching algorithm. We can do prototype matching by correlation. We've done this in one of the lectures, but this is going to become more clear. We're going to talk about correlation, the use of correlations for pattern matching and consequently recognition. In matching structural prototypes, honestly, I've never seen any application of matching structural prototypes, but it doesn't mean that there isn't. I don't have all the knowledge of the world. So, well, the first algorithm is this one I've seen in many places, and it's very very popular. Is the minimum distance classifier. So, what do you do? You get as prototype vectors the mean vector. All right, let me just mark that. So as prototype vectors, you're going to use the mean vector of each of the pattern classes. So of course, in this case, it's not learning, but it's a supervised process where you have to be given a set of known classes, right? So it's a supervised process, and then the prototype is just going to be the mean vector of each of these classes, right? If I have J classes, such as if I get the iris setosa, where is the iris setosa? Here. How many classes? I have basically three: the petal length, petal width, sepal length, and sepal width. And I have basically, I'm going to get as feature vectors the mean value for petal length of each one of these iris setosa, virginica, and versicolor, and also the width, and also the same thing for the sepal. So Nj then is the number of pattern vectors of the jth mean vector. Cj is the jth pattern class, such as iris setosa, I can't pronounce these names. And we are going to use the Euclidean distance to determine similarity. That's going to be the distance of an unknown pattern X to each class Mj. That's going to just be given by the normal Euclidean distance as the usual Euclidean distance. So we've seen this today, right? Can you recall the first lousy pictures that I've drawn here? Remember when I had a number of distinct classes, distinct points? But in this case, the patterns are given. So it's like I gave a number of examples of stars, circles, and squares. And what I do, I just get this number, a bunch of points, and get the mean value. Get the mean value of these classes. And then what I do, if I have a new image, so I want to classify a new image that's given by, I don't know, the conveyor belt in my industry and with a video camera, then this image, something like that. I don't know what it is. So I get the features, extract the features from this image, and this falls here. I just get the minimum distance. I get I measure the Euclidean distance from every center, from every mean value to that, and get the smallest. That's going to be I star, right? Easy peasy. So then using the Euclidean distance to determine similarity, the distance of a known pattern to each class mean value. Then the classifier assigns a class Ci to an unknown pattern X if the distance from the unknown pattern X to the class I is less than the distance of the unknown pattern. Sorry, pattern to to any other of the classes, any other classes that obviously any other that's different from this one, right? Okay, so basically selecting the smallest distance is equivalent to evaluating these functions, right? So the book doesn't do the derivation for this, and it sets up as an example, as an exercise. It's easy to see. If you want, you can do this exercise, but for us, that we have so much still to see that we're gonna just assume this as truth, right? So basically, selecting the smallest distance is equivalent to evaluating these functions for all classes. And assigning an unknown pattern X to the class whose prototype yields the largest value of D. All right, so we're gonna solve these equations to finding the largest value of D. Then what we want to get is the decision boundary separating these two classes, right? These two classes. So the decision boundary is nothing more than getting these D functions representing class I and class J. The distance between them is going to be the difference between this stuff, right? If I just put substitute these equations here into here, and then they are going to have equal distances if this equation here is equal to 0. So we want to solve this equation. When we solve that, what we find is exactly this line here separating the two classes. This line here separating two classes. Let's get an example to see this in numbers, right? So basically, let's consider the iris data set, but only with two values for each vector, right? So each feature vector, the petal width, and the petal length. Why we're just choosing two values? Because then we can see this in the two-dimensional space. If we use the four values for petal width, petal length, sepal width, sepal length, we cannot draw it. We still don't know how to draw in 4 dimensions, right? It's a multi-dimensional problem. So getting then only for petal width and length, the mean values of these feature vectors will be the mean values of the petal width for class 1, which is iris versicolor. I'm calling that the class 1 will be the iris versicolor class. So the mean value will be the mean value of the petal width and the mean value of the petal length. And for the iris setosa as well will be the mean value of the petal width and the mean value of the petal length. Now we just apply that equation then for the versicolor here, substituting the values, and for the iris setosa. And finding the equation, substituting that in the equation for the boundary, that's this one. That's this one. Then we get this value here. When this is equal to 0, that's going to be exactly this line, And this line is what we call decision boundary of the classifier. Basically, what your statistical classifier or any statistical classifier that you want to derive, that you want to use, is going to find this boundary. In this case, this is a linear boundary. You can have non-linear boundaries. You can have curves, very complex curves for classifiers. But this one, you just learned how to apply the Fisher linear discriminant analysis. This is exactly what, in a nutshell, there's more to it, but in very basic terms, this is the linear discriminant analysis. So what do we gain with this? finding this decision boundary is exactly that. If you get a new pattern vector, so a new, let's stop talking about image, a new pattern vector, so a new set, a new example of a flower. I want to see whether this flower is an iris versicolor or an iris setosa. I don't know anything about flowers, just that you can't eat them. That's the only thing I know about flowers in general, right? You can't eat flowers. There are flowers that you can eat, but I don't know how to recognize. So, but I want my system to recognize whether this is an iris setosa or an iris versicolor. So I get the pattern vector from a flower that I found on the field, measure the found, and put that in the equation, in this equation. So if the result is positive, substituting for x1 and x2 here, where x1 is the petal width and x2 is the petal length. If the result is positive, it's gonna be an iris versicolor class. It will be a flower of the class iris versicolor. If the result is negative, it's gonna be a flower of the kind iris setosa. This could be the decision boundary between my life and death, right? So if I could eat an iris versicolor, but if I eat an iris setosa, I could die of food poisoning, right? So this is basically it's very useful, at least for me. Doesn't know anything about flowers. Okay, so minimum distance classifier is very good if the distance between the means of your class is large compared to the spread or randomness of each class. This is clear, right, people? This is very clear. So in this case, so the distance between the means is very large compared to what? Compared to the spread of the classes. This one is quite well contained. This one is more spread out. But imagine that I had more points here, and I had more points of this kind here. Right? It may happen. It may. So in this case, your minimum distance classifier it will have a hard time to actually distinguish these classes. So we're going to have to use other methods, some more advanced methods. But as I said, in an industrial situation or in some of the natural sciences situations where you have very clear distinctions between your classes, you can use the minimum distance classifier easily. So some keys to the accurate recognition. Keys to accurate recognition. Right. So that's difficult. So that's the human input. So you should specify the features. You should find good features. You should find very good discriminant features. In this case, this was the job of Fisher in 1936 to find these classes, right? So these features, what are the features? These features. So the petal length, width, sepal length, and width. So this was Fisher who found this. So, but if I get the color, for instance, if I assume that the color was a distinguishing feature, that could be a mistake, right? The minimum distance classifier wouldn't be able to do anything with colors if it's not a good discriminant feature. Okay, so there's the hard part of the problem is given to the human input. So you should be able to select features that would imply a wide separation between the means, and that's usually not a simple task to do. Right. So maybe this is a good point for a pause. Let's I will stop the recording and divide this lecture in two, as I've been doing, and give it 5 minutes for us to drink some water. I will stop the recording now and get back here in